All right, guys, welcome. Business Cal, this is section 9.1. We will learn about limits today. Yeehaw, the informal definition of a limit and what it means, right? So we will start off by analyzing a function, and we're going to look at the given function f of x equals x plus 1. Given a domain restriction as well of x cannot equal 1. So we're going to analyze this function at the x value that we cannot be. So this is how a limit's going to work. So as x gets close to a number, what we want to know is the behavior of y. So as we get close to x, we want to know what number is y getting close to. So we will analyze that behavior by the use of xy charts. And when we deal with limits, we look at a limit from the left side of a number, and we look at the limit from the right side of a number. So once again, the number we are going to analyze this function at is going to be 1. Okay. So with that being said, to analyze the limit, we will start with a left-hand limit. So the first xy chart here is going to represent the left side, all the numbers to the left of 1. Okay, so I'll write that in there. This is going to be the limit from the left side. And once again, to explain what it means to approach a number from the left, I'm going to plot 1 on this graph. So there's 0 and there's 1, right? There's 0 and there's 1. If you approach a number from the left, you are choosing numbers smaller than 1. So if I approach 1 from the left, I am choosing all of these numbers that are headed towards negative infinity. So this is what it means to approach a number from the left side. So I will approach 1 from the left. But we'll see what happens when we land on 1, okay? So that's what it means to approach numbers from the left side of a graph. You approach from negative infinity. Okay, well, let's look at that. Let's choose some numbers. We don't have to fill up this whole XY chart. Let's choose some numbers to the left of 1. Let's start at negative 2, right? Which is here, negative 2. Then let's start at negative 1. Then let's choose 0. And now let's choose numbers that get really, really, really close to 1, but are not 1. So we'll start with 0.5, 0.75. How about 0.85, 0.95, 0.99, 0.999, and let's go ahead and choose 1. Okay, so again, these are all numbers to the left of 1. So this is a limit from the left. Okay, so now, of course, we have to take these numbers and plug them into the function we are analyzing, which is x plus 1. Well, fair enough. We plug all these numbers in for x, and all we have to do is add 1 to them. So if we plug it into x plus 1, I'd get negative 1, 0, 1, 1.5, 1.75, 1.85, 1.95, 1.99, whoops, too many 9s, and 1.999. Okay. And then eventually we see that as, okay, listen closely, right? So this is how we work a limit. So we see as these x values get closer and closer and closer to 1 from the left side, we see that my y values are getting closer and closer and closer to what number? Well, if you said 2, that answer is correct, right? But then we run into an issue here, right? Yes, I'll put 2 here, but can y actually be equal to 2? And that answer is no. Because if you look back at our domain, it says in the very beginning, we can use x plus 1, but the only x value that this function will not exist at is at 1. So this means that as we get closer and closer to 1, y should be equal to 2, but since the domain says we can't use 1 at all, this point, 1, 2, is going to be considered undefined. Let me write that in there. Let's see. Okay. So let's run it back. So what we're going to say is that as we approached 1 from the left side, so as our x values approached 1 from the left side, so as x got closer and closer and closer to 1, our y values got closer and closer and closer to 2. But because of our domain issue, y cannot be equal to 2. Which means if I were to plot this on the graph, how do you draw an undefined point? What type of circle? Open or closed? And what we'll see is that at the point 1, 2, we are going to have an open circle. So here's what we look like. -2, wait a minute, -1, 0. So this is what the left side of the graph would look like. So what I'm saying, again, now graphically, without looking at the chart, what I'm saying is that as x gets closer and closer to 1 from the left side, y is getting closer, oh, different color. Y is getting closer and closer to 2. But will y ever touch 2? And that answer is no, because that's how a limit works, right? The limit says it exists at 2, but the function may not. The point may not exist. So these are things to keep floating in your head when we get to the continuity lesson in 9.3, I think. Or is it 9.2? Either one. So for now, we are learning the informal definition of a limit. So let's learn how to write limit notation. Okay, so we approach this limit from the left side. So what we're going to write is that the limit as x approaches 1 from the left, this little minus sign means we approach a number from the left side. And that definition's on the next page, right? So we say the limit as x approaches 1 from the left of the function x plus 1 will equal 2. There it is. Our XY chart proves that this is equal to 2. But again, Can the function be exactly on 2? Can the y value be exactly on 2? No, because it says our domain is x can't equal 1, and therefore a y value can't exist with it. So the thing that should be popping in your head is, say, how can a limit exist at a certain number, but a function cannot? So once again, keep that rolling in your head. We'll explain more of that when we get into continuity. Okay. So that is a limit from the left. Now let's look at a limit from the right side. So what does it mean to approach a number from the right? This means you use all the numbers bigger than it. So again, we are approaching 1. And if we want to approach 1 from the right side, we use all the numbers starting from positive infinity, meaning all the numbers are bigger than 1. So we come from positive infinity, and we stop as we get really, 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 really close to 1. So let's see what that looks like on the XY chart. Let's look at the numerical values, right? Okay, so now we have the right side. Oops. Okay, and now let's choose numbers to the right of 1, which means let's choose numbers bigger than 1. But again, let's not get too crazy. Let's start with 3. Then let's start with 2. And then let's start with 1.5, 1.3, 1.2, 1.1, and now 1.01 and 1.001. And then finally ending, let's make this match up. I'll say 1.0001, and then finally ending on the number that we can't use, which is 1. Okay. Once again, we are plugging numbers into the function x plus 1. So let's plug these numbers in. We get 4, 3, 2.5, 2.3, 2.2, 2.1, 2.01, 2.001, and 2.0001, finally ending at 2. But once again, can y actually be at 2? And the answer again is no, because we cannot use the x value of 1. We can only get really, really, really close to 1, but never touch it. Okay, and once again, this is going to be considered an undefined point. Okay. So let's look at the graph. So the rest of my function would graph out to something like this, which means what we did on the number line, on the XY charts, says as we approached 1 from the right side, we saw that y was getting closer and closer and closer to what number? And if you guessed it, that number would be 2. And again, let's verify from our XY chart. Look at my x values for the right side. We said that as x approached 1 from the right side, y started to get closer and closer and closer to 2. I mean, in reality, 2.00001 is just 2. But once again, because of the domain issue, we cannot be on 2. Okay, so we've seen it graphically, we've seen it numerically. So what we're going to say is that the limit of x plus 1, as x approached 2 from the, as x approached 1 from the right side, the limit will be equal to 2. So let's write that down in the notation. All right, so we'll say the limit as x approaches 1 from the right side. That little plus symbol means we are approaching the number from the right side of a graph. Okay, of the function, x plus 1 will equal the number 2. So we say the limit as x approaches 1 of the function x plus 1 will equal 2. So once again, we have a limit that exists and a point that is undefined. And this is okay. Just make sure you are good with the terminology. All right. And now, the big picture here. So we now see that the limit from the left is 2. The limit from the right is 2. So what we say is that if the left-hand limit and the right-hand limit are equal, then the limit from both sides of a number must also be 2. So what we're going to write here is that one last limit notation for you. Since the left-hand limit is 2 and the right-hand limit is 2, this means that, the limit as x approaches 1 from both sides, now you see there is no plus sign, there is no minus sign on the 1. We leave it alone. If you just see a number by itself, this means you are approaching it from both sides, okay? So this says the limit as x approaches 1 from both sides of x plus 1 must also be equal to 2. And this is called the informal definition of a limit, which we have proven by left-hand limits and right-hand limits. And there is that definition for you below, which probably doesn't look like English to you, right? So this says the limit as x approaches some number c for the function f of x will equal some number L. That's exactly what we just did. So we said the limit as x approaches 1 of x plus 1 will equal 2. This is the same thing as that. Just plug in some numbers, right? Or you could say, as y approaches 2, x approaches 1. Or in definition terms, as f of x approaches some number L, x is approaching some number c. So that's exactly what we did. If you look at the graph, we approached 1. So let me draw there. Fun glitter drawing. We said, as we approached 1 from the left, and as we approached 1 from the right, we saw that y was getting closer and closer to 2. And that is the definition of a limit. Like I said, in English, as x gets close, really, really close to a number, all we really want to know is what is y doing? What is y up to? What number is y approaching? And for this one, we said as we approached 1 from both sides, y got really, really, really close to 2. But it never landed on 2. There you go, guys. That is the definition, informal definition of a limit. And yes, more practice, right? But this is how we dig in. This is how we analyze the limit of a function, okay? All right. Next page, more definition, but it's going over everything we did already. Look at that, the definition of a left-hand limit. So if I zoom in, look at that notation. It says the limit as x approaches some number c from the left side of f of x will equal some number k. That is exactly what we did there in the first limit. We said, as x approach 1 from the left side, the limit of x plus 1 is 2. And that is the left-hand limit. It means that you approach a number from the left. It means that all the values of x are less than that number you're approaching, right? We were approaching 1 from the left. This means that all the x values were less than 1 because they were on the left side of the graph. Okay. Look at the next definition, the right-hand limit. We know that already. We did it without even knowing the definition. This one says the limit as x approaches c from the right side of f of x will equal some number L. Once again, we did that already. Right there. That says the limit as x approaches 1 of x plus 1 will equal 2. We did it already. And there you go. So the right-hand limit means you approach some number c from the right side, and those x values will be bigger than that number you are approaching. So x, all the x values were greater than 1 on that last example. Okay. So those are the definitions of a right-hand limit and a left-hand limit. And did we need them? No, because we did them already on the first example, right? Same with the next theorem, right? Oh, first, let me see. Look at this little statement here. This says, if no direction is specified in a limit statement, this means we assume that we take the limit from both sides. So just like we had our final limit, there was no direction, there was no plus or minus. So this means we must take the limit from both sides. So that's all that says. Okay, and then next, the existence of a limit. For a two-sided limit to exist, the limit from the left and the limit from the right must exist and be equal. We did that already, guys, right? This says the limit from the left is equal to the limit from the right. And if they are equal, this means the limit from both sides is also equal to that same number L. Once again, that's everything we did in the first example. Look at this. All right here. The limit from the left was 2. The limit from the right was 2. This means that the limit from both sides must also be 2. Now what happens if the limits were different? What if the left-hand limit was 1 and the right-hand limit was 2? This means the limit from both sides, in the words of Lindsay Lohan, the limit does not exist. Which we'll get into an example right now, I think. Oh yeah, perfect. Okay, so our next example is to analyze a limit graphically. So we are given the graph, and we want to analyze this limit at a specific number. So for all these examples, it's asking us to analyze the limit at 2, when x is 2. So first up is, what is the limit of f of x as x approaches 2 from the left, Remember that little minus sign means from the left. So let's find out. So look at the graph. We are approaching 2 from the left side. So as x approaches 2, we see that y starts to approach what number? So as x approaches 2, y slowly starts to approach 3. Not 3. Oh, I'm way off. My bad. Oops, wrong one. Y starts to approach 2. There you go. I was looking at 1. My bad. So it's reverse. Okay. So once again, as you approach 2 from the left, y starts to approach 2. So you can track your x and y values together. So as we approach 2, as x approaches 2 from the left, y starts to approach 2. So the limit of f of x as x approaches 2 from the left will be 2. There's that. Okay, and then the next one is, what is the limit as we approach 2 from the right side? Well, now we approach 2 from the right side, and again, track your x values with your graph, so we'll be looking at this graph above. So as we approach 2 from the right side, we see that your y values get closer and closer to 5. All right, let's do it again. As you approach 2 from the left, you see that your y values slowly start to approach 5. Okay, so this means the limit as x approaches 2 from the right will be 5. Okay, now C. This is going to use the theorem above. It says, what is the limit as x approaches 2 from both sides? Well, by the definition, the left-hand limit and the right-hand limit at 2 must be equivalent for the limit to exist from both sides. So look at this. Our left-hand limit is 2. Our right-hand limit is 5. Does 2 equal 5? Not at all, right? So the left-hand limit is 2. The right-hand limit is 5. They are definitely not equal. And since the limit from the left and the limit from the right are not equal, we get to write that the limit as x approaches 2 from both sides of f of x does not exist, because the limit from the left and the limit from the right at the same number are not equal. Their y values, their limits are not equal. Okay, and the very last one has nothing to do with limits. It has everything to do with points that are defined and undefined. So for the very last one, what this one says is, when x is exactly 2, what is the value of y? When x is exactly 2, what is the value of y? Now, when x is 2, and if we go up on the graph, we have a y value here, and we have a y value there. You have a y value at 5, and you have a y value at 2. Well, when it's asking for a y value, we only state defined points. Remember that a closed circle is a defined point. That is defined. An open circle is undefined. Oh, am I in the way? I think so. So we only state y values that are defined. So for D, we say when x is exactly 2, the value of y is also 2. And there you go. That's it. So now the things that should be going on in your head is, how can a limit not exist, right? How can a limit not exist, but a point can be defined, right? Which means if we went back to the very first problem, it's actually the opposite. This first problem says our limit exists, but our point is undefined. These are just things to think about when I talk about continuity in the next lecture. So keep these ideas rolling in your head. These are good ideas to have. Good thoughts, ideas to have. A limit can exist, but a point can be undefined, or a limit cannot exist and a point can be defined. And maybe we can have the unique situation of a limit existing and a point being defined. That can happen too. But if that happens, then the problem's way too easy, and we don't want that. All right, moving on. That's how you analyze a graph by the use of limits, okay? All right. And now we have an algebraic approach to limits. Of course, we can apply algebra to everything. Algebra is the foundation for calculus. So remember, if calculus seems too hard, just remember that it's based on algebra. And if you know your algebra, you're gonna be just fine. Okay, so let's roll through these limit properties. So it says, let f and g be two functions and assume that the limit of f is equal to L and the limit of g is equal to some number m. Then we'll have the first property. This first property is the constant rule for limits. This says the limit as x approaches some number c for some constant k, that limit will equal k. To put it simply, the limit of a constant is the constant. So, and I'll write example limits for you over here. This says, if I have the limit as x approaches 0 of the number 5. And again, knowing your definitions is important as well. What does it mean to be a constant? A constant is just a number without a variable. That's it. So you can just say a constant is a number. 5, 6, 100, 1,000, 1 million. As long as it doesn't have a variable attached, it is considered a constant. So the limit of a constant will always be a constant no matter what number x is approaching. So the limit of 5 will still be 5, no matter what. If it was the limit of 10, the limit would still be 10, no matter what number x approaches. X could be approaching infinity, and the limit would still be 5. Okay. 2, the limit as x approaches c of x will equal c. This is called the direct substitution property. This says just plug in that number for x, right? That's all this says. So we can write if I have the limit as x approaches 2 of x, all this says is, hey, plug in 2 for x and we're done. And that's it. So whatever number x is approaching, plug it in for that value of x. All right. The third property says the limit can be applied over addition or subtraction to multiple limits. So this says the limit of f of x plus or minus g of x can be split into the limit of f of x plus or minus the limit of g of x. That's it. So let's say if I have the limit as x approaches 1 of x plus 5. There are 2 terms inside the parentheses, which means I can split this into 2 limits. I can make this the limit as x approaches 1 of x plus the limit as x approaches 1 of 5. That's it. And it doesn't matter if it was over subtraction or addition, I can split it into multiple terms. All right, there you go. And then you can simplify from there, but I want to keep going through these properties. I'm just showing you how they work. Number 4 says the limit as x approaches c of some number k times f of x. All this one says is take that k, move it to the outside of the limit, and multiply it in later. That's it. So if it's a coefficient, you can move it to the outside. So let's see what that looks like. If I said the limit as x approach 0 of 5x squared, I guess 5 is my special number today, sure, of 5x squared. All this property says is, hey, take this 5 and move it to the front. So you'll get 5 times the limit as x approaches 0 of x squared. That's it. If it's a coefficient, move it to the front. That's all that property says. And then simplify. All right. 5 says the limit can be applied over multiplication of multiple terms. This says the limit of f of x times g of x can be split into the limit of f of x times the limit of g of x. So let's see what that looks like. Let's say the limit as x approaches, let's just keep it 0. I can even keep it c, it doesn't matter. So the limit as x approaches 0, let's say I have x times x plus 1. I have 2 terms inside the parentheses, which means I can split this into 2 limits. And remember, I could have more terms if I had 3 terms, if I had 4 terms. However many terms are in there tells you how many times you can split the limit. So I can rewrite this as the limit as x approaches 0 of x times the limit as x approaches 0 of x plus 1. That's it. I can split it into multiple limits, no matter how many terms are in there. Okay, 6. Well, if I can definitely split or apply limits to addition, multiplication, the number 6 says you can apply the limit to division as well. So the limit of f of x over g of x can be applied to the limit to the numerator and denominator separately. The limit of f of x over the limit of g of x. And once again, another example. Let's say I had the limit as x approaches 1 of 5 over x. Well, now I can split this and say the limit as x approaches 1 of 5 over the limit as x approaches 1 of x. That's it. I applied the limit to the numerator and the denominator separately. Okay. Very last one. The limit as x approaches c of the nth root of some function. All this says is take the limit and apply it to the inside of the radical, the inside of the root, and simplify. So for number 7, let's say I had the limit as x approached 0 of the square root of x plus 1. All this property says is take that limit and put it inside the radical. Which means I get the square root of the limit. I need more room. Let's see. I'll zoom in more. There we go. Of the limit as x approach 1 of x plus 1. That's all it says. Take the limit, put it inside the root, no matter what power of root it is. Square root, cube root, fourth root, 100th root, whatever it is. Oh, it's not 1, it was 0. Either way, you get it. There you go, 0. Okay. And that's how those properties work, which means we can now apply them to the next problems. Theorem 3 says, the number 1 of theorem 3 says, the limit as x approaches c of f of x will equal f of c for any polynomial function. So this is just like the property above that I called direct substitution. All this says is, hey, take that limit and plug it in. That's it. Take it and plug it in. That's all you have to do. 2 says, the limit as x approaches c of r of x will equal r of c for any rational function with a non-zero denominator. So what this means is if you're plugging a limit into a fraction, just be careful that you do not zero out the denominator, because that is a no-no. Don't worry, the next examples should touch on it. So let's get started. Let's apply these properties, and let's get moving. So first up, use limit properties to evaluate these limits. So what we're going to do is I will, let's see, I'll show you how the limit properties work, and then we'll go from there. So there are 2 terms inside these parentheses. So what we're going to say is the limit as x approaches 3, since there's 2 terms, I can split this into 2 limits. The limit as x approaches 3 of x squared minus the limit as x approaches 3 of 4x. Now, using these limit properties, I can now take this 4 and move it to the front because it's a coefficient. Let me move it to the front. So that's the next write-up. I now get the limit as x approaches 3 of x squared minus 4 times the limit as x approaches 3 of x. Look at that. I just took that 4, moved it out front, and now let's apply the direct substitution property, which means let's take this 3 and just plug it in for all the x's. Which means you'll get 3 squared minus 4 times 3, which will give us 9 minus 12, which gives me -3. So what we say here is that the limit as x approaches 3 for the function x squared minus 4x will be equal to -3. That's it. Now, if you're wondering, do we have to split it up all the time? And do we have to separate it all the time and move numbers this way and that way? The answer is no. The answer is, why didn't we just plug in 3 from the beginning? If we plugged 3 in from the beginning, we would have been right here and done. Crazy, I know, right? So those properties are there to show you that you can split things up if you need to, if it looks too difficult. But if it doesn't look difficult, just plug the number in and we're home. Yeah, whoa, right? So that's what we'll do with the next ones. Let's just start plugging numbers in and see what happens. Number 2, the limit as x approaches 1 of 5x plus 4. Hey, let's just plug in 1 and see what happens. You'll get the square root of 5 times 1 plus 4, which will give us the square root of 9, which will give us 3. Sometimes, guys, it's that simple. Is calculus that simple? It sure is. Isn't that right, Ted? He agrees. Okay. Moving on. Do it again. Find the limit as x approaches 4 of x minus 2 over x. Hey, it worked last time. Let's just plug in 4. Let's do it. You will get 4 minus 2. Just was too ugly for me. There we go. Let's try that again. 4 minus 2 over 4. We plug it in. Let's simplify. 4 minus 2 is 2. 2 over 4 is 1/2. Beautiful. That's it, guys. Sometimes just plugging the number in, it works. Simplify it, done. Get on with your life, right? Okay. Let's do it again. Let's plug in 2. Since we think calculus is so easy, let's just plug in 2. It works for all the other ones, right? So you'll get 2 squared minus 4 over 2 minus 2. Simplify. You get 4 minus 4 over 0. Bum, bum, bum. And then you get 0 over 0. Now, does 0 over 0 equal 0? And that answer is no. No, no, no. 100, 1,000 times no. 0 over 0 is not 0, right? And 0 over 0 is definitely not 1 as well. And if you're wondering where I got 1 from, well, isn't any number over itself 1? So shouldn't 0 over 0 be 1? No. So if you ever run into this issue where your denominator zeroes out, this means you have run into a specific type of form. This is called an indeterminate form. And if you ever run, oh, can't see it because I'm in the way. If you ever run into an indeterminate form, this means go back and start over, because we probably missed something. So do not pass go. go straight to the problem again, or calculus jail, either one you want. So let's take a look back at the problem, and if you ever come across an indeterminate, this means you can fix it. How do you fix it? Well, again, calculus is highly algebra-based, so you have to look at this in an algebraic way. Look at the numerator, x squared minus 4. This has a specific name. This polynomial is known as a difference of squares, right? It's known as a difference of squares. Remember, if you ever came across a squared minus b squared, it would factor to a plus b, a minus b. And these are things you're gonna have to notice. Your main thing should be, how can I fix this algebraically? I must think algebraically, and it can be something as simple as factoring, okay? Something as super easy as factoring. And this one we can fix by the algebraic method of factoring. So let's go ahead and factor it. So we're gonna say the limit as x approaches 2 of, and now we're gonna factor the numerator. X plus 2, x minus 2 over x minus 2. And now what you see on the next step is you can simplify more. You see that you have an x minus 2 here and an x minus 2 there. So those can cancel, which leaves you with a new limit of x plus 2, where now it is safe to plug in 2. If we plug in 2, you'll get 2 plus 2, which will give us 4. And this answer is definitely way different from that answer of 0 over 0. So once again, if you ever run into an indeterminate form, you have to start back and look at the problem and think, how can I fix this algebraically? And if you cannot fix it algebraically, well, then you go back to the very first page and make those gruesome XY charts to figure it out. But sometimes algebra is a lot faster. Okay, those are things just to look out for. All right, let me erase that. There we go. Okay, let's do it again. 5. Find the limit as x approaches 3 of x squared minus x minus 6. And again, let's go off the thing we know. Plug the number in and hope for the best. And if we get something bad, then let's go back and start over. And we plug in 3, you'll get 9 minus 3 minus 6 over 5, which will give us 9 minus 3 is 6, 6 minus 6 over 5, which gives us 0 over 5. Oh, stressful, stress time, stress time. 0 over 5 equals 0. Do not mess that up, people. 0 over 5, 0 over any number is always 0. Now, let's say on the chance that you get 5 over 0. Once again, can you have 0 in your denominator? That answer is no. But this has another form. This is an indeterminate. Indeterminate is known as 0 over 0. This is called undefined. So, know the difference. All right. Okay, cool. And again, this one definitely could be factored. If I factored this one, you'd have the limit as x approaches 3 of x minus 3 times x plus 2 over x plus 2. Your x plus 2's would cancel, giving me the limit as x approaches 3 of x minus 3. And if I plugged in 3, you'd still get 0. Crazy, I know. Purely algebraic, it's beautiful. I know you're not math majors, and I know your algebra is not so hot, but that's why we're in business, Cal. I'm here for you. All right, last one. This one is an exercise on reading piecewise functions and connecting restrictions to limits. Connecting restrictions to limits. Let me pause for a moment. Okay, pause over. So again, taking piecewise functions and connecting them, connecting their restrictions with limits. And if you have no idea what a piecewise function is, well, that's what you are looking at. This is called a piecewise function. It is made, a piecewise function is a function made of multiple pieces with multiple restrictions. And learning how to read a piecewise function is very important. Okay. All right, so with that being said, we are going to use the definition of a left-hand limit and a right-hand limit and connect them to the restrictions in the piecewise function. So for the very first limit, this says, what is the limit as x approaches 2 from the left? Remember, if I were to draw this on a graph and put 2, if we approach 2 from the left, this means we are coming from negative infinity, which means all my x values must be, all of these x values must be less than 2, right? So if we're approaching 2 from the left, we have to look at these restrictions and see which one does the limit match. And if we approach 2 from the left, this means all my x values must be smaller than 2. They must be less than 2. So we will connect this limit to the first restriction in the piecewise function, which means it allows us to use the first piece. Okay, so with that being said, what I write next is the limit as x approaches 2 from the left. since we are able to use this restriction, or since we match it to this restriction, this means we get to use this function. So that's what I'm going to write with my limit. The limit as x approaches 2 from the left of x squared plus 1, which means all you have to do now is plug in 2. 2 squared plus 1 gives me 4 plus 1, or 5. So what we say here is that the limit from the left at 2 is 5. That's it. That's matching a limit to a restriction in the piecewise function. And doing so tells you which function you can use. All right, the next one. The limit as x approaches 2 from the right. Once again, I drew a graph. There's 2. Here's infinity. If you approach 2 from the right, we are coming from positive infinity, which means all these numbers have to be greater than 2, which means this limit will match to that restriction, which means we will use that function. That's how it works. Match it to the restriction, and it will tell you what function to use in the limit. Okay. So what we write is the limit as x approaches 2 from the right of x minus 1, which means now just plug in 2. You get 2 minus 1. Actually, I don't need parentheses there. I need them on the 2. 2 minus 1, which will give us 1. Okay, there it is. The limit from the left is 5. The limit from the right is 1, which means, you guessed it, number 3 wants the limit from both sides at 2. And in order to have a limit from both sides at 2, the left-hand limit at 2 and the right-hand limit at 2 must be equal. So our left-hand limit is 5. My right-hand limit is 1. Do those match? Does 5 equal 1? And the answer is no. Therefore, in the words of the great Lindsay Lohan from Mean Girls, the limit does not exist, because the left-hand limit is 5, the right-hand limit is 1, and they are not equal. Okay. And the very last one. Again, this is just like the very first example we did, or the second example. All this says is when x is exactly 2, when x equals 2, what is the value of y? That's it. So we're looking for a restriction that allows us to be exactly equal to 2. And if you look at the top, which of these restrictions allows us to be equal to 2? And if you guess the first restriction, that is correct, because this says x can be less than or equal to 2, which means we can use this function and plug in 2. That's it, guys. And we already did that work. We know what happens when you plug in 2. Oops. You'll get 5. So that's it. If I come down here, all we say is that f of 2 is 5. Yeah. There we go. And that's it, guys. That is limits. That is the informal definition of a limit and how to evaluate limits and look for things algebraically. All right. See you at the next lecture.